Okay, so let's get started. Today, I want to apply spectral sequences to prove some of the theorem that we proved earlier, okay? Like the check-theorem isomorphism and the various tic-tac-toe lemmas. And you will see that it's much simpler using spectral sequences, and it provides a uniform method, for calculating the cohomology of a double complex. Okay? So first, let me just write down the theorem that we proved last time. So for every first quadrant double complex, okay, K, there is a spectral sequence ERDR, okay? And okay, so we have to filter this double complex, and we filter it by P. So this is K0 and then K1 and so on. Okay, so yeah, I need to say filter by P for every first quadrant double complex filtered by P. There's a spectral sequence such that E1 is HD of K, and E2 is H delta HD of K. And DR, okay, it goes from ERPQ to, okay, so remember that E2, in E2, D2 goes down by 1 and goes across by 2. Okay, so D2 looks like that. So D2 goes across by 2. In general, DR goes across by R, and it goes down by R minus 1. So you have Q minus the quantity R minus 1, therefore it's Q minus R plus 1. Okay? Such that the spectral sequence converges to the total cohomology. So we have this spectral sequence such that this is true and converging to HD of K. And what that means is that eventually all the E's become the same. So in fact, we know when it becomes the same because say in degree n, so these are elements of degree n, and you see that if the filtration, let's say, just make this degree 2, okay? And then here is K2. And so you see that the filtration will have length 2. It will terminate, at K2, and then K3 in degree 2 will be 0. All right, so for R greater than N, for R greater than N, then the filtration in that degree is 0, and so yeah, ERN is equal to ERN plus 1, because all the differentials will become 0. And equal to ERN plus 2, and so on. Just a minute. No, sorry. No, the degree is fixed. Yeah, the degree is fixed. It's the R that's changing. Okay. Yeah. Okay. So as you turn the page, R is a page number. As you turn the page, the group will not change, and that stable value is E infinity in degree N, okay? And to say that it converges to the total cohomology means that this E infinity is the associated Grady complex of the total cohomology. Okay? So now the associated Grady complex, right? It's, you have a filtration on the cohomology. So the cohomology is also a double complex. And this filtration K induces a filtration on the cohomology also by P, right? So, okay, and so the associated gradient complex of the total cohomology is the direct sum of f of P over f of P plus 1, okay? And E infinity N will be these boxes. So it will be E infinity. Okay, so these boxes should have degrees that sum up to N. So it's P, N minus P, and you take the sum from P equal to 0 to N, okay? Yeah. And this also goes from P equal to 0 to N. Okay. So that's the theorem. Now, you have a double complex, so it has 2 degrees, and we filter by P, but we could also filter the double complex by Q, and that will give us a second spectral sequence. So, yeah. So we can filter by Q. So this would be K0 prime. K0 prime is everything, and then K1 prime, and so on. We can filter by Q, okay? And all the arguments before will go through. So now we'll have a second spectral sequence. So if we filter by Q, we get a second spectral sequence. ER prime, VR prime, such that, okay, E1 prime is equal to, what should E1 prime be? I mean, we're reversing P and Q. So that means we are making a reflection about the diagonal. Yeah, it should be H delta. Okay. Instead of this vertical differential, now it should be the horizontal differential. Okay. So E1 prime is H delta of K. And then E2 prime would be HDH delta. Because we're flipping the vertical and the horizontal. Okay. And dr prime should go from ERPQ to where? Okay, previously we go horizontally, R boxes. So now we should go vertically, R boxes. So that means Q should be increased by R, okay? And P, well, we used to go down R minus 1. Yeah, we go down R minus 1. Now we should go horizontally to the left by R minus 1. So P should go to P minus R plus 1. Okay? Yeah. Uh-huh. And again, okay, we get this. Yeah, well, I mean, this doesn't really, depend on P and Q right here in this statement. So E infinity is still the associated Grady complex. Yeah, so, and E infinity, E infinity in degree, well, E infinity is still the associated Grady complex. Yeah. Okay, yeah. Okay, so, well, that's great because what this says is that that you can compute, the associated Grady complex of the total cohomology in two ways. Okay, you can compute it filtered by P or filtered by Q, and the two ways should be equal. Okay, yeah. Hmm? In the first line, if we filter, good, yeah, right. If we filter K by Q, yeah, that's right, yeah. Okay, we used to filter by P, and now if we filter K by Q, thank you. Okay, then we get the second spectral sequence. Okay, so now let's use the spectral sequence to compute, to prove the check-Durham isomorphism. So in the check-Durham isomorphism, our double complex is the check-Durham complex. So KPQ is the pico-chains, of an open cover, but okay, we should start with an open cover. So let U be any open cover of a manifold M, and then KPQ is the group of pico-chains of the open cover with values in the Q forms. And yeah, okay, so let's compute the two spectral sequences. Yeah, so okay, so the double complex looks like this. Okay, so let me see. So here is C0 U omega Q, C1 U omega Q, and so on. And this CP U omega Q, it means that it is a direct product, of omega Q over the P plus 1 fold intersections. Okay, yeah. So this is K. So let's first compute E1 prime. E1 prime is H delta. Okay. What is E1 prime gonna be? You take each row and you take the delta cohomology, the check cohomology. But what do you know about each row? Each row of the check-Durham complex. Yeah, it's exact except for the first term, right? Because it's a Mayer-Vitora sequence without that first term, and that first term is, it's the global forms, right? Here in the zeroth column, these are the Q forms on each open set. And then this is a difference map. So the kernel would be global forms. There'll be like Q forms that agree on the overlaps of open sets. So it'll be global forms. Okay, so you see that this is exact except the first term. Here you need the kernel of omega, and the kernel of omega is the global forms. Okay, and then because it's exact everywhere else, you have 0. Mhm. So E1 prime, yeah, E1 prime is equal to H delta. Mhm. So H delta gives you the global forms. All right, yeah. And then now we take E2 prime. So we take HD of this. Let me see. I don't know. Well, I think I can erase that part there. Let me leave the theorem there. So E2 prime is HDH delta, and that is going to be the cohomology of the 0th column with the differential D, and that's the Ram cohomology. So HDH delta looks like this. Uh-huh. Okay. And now oh yes, now we need D2 prime. Uh-huh. Okay, now D2 prime, where does it go? Well, D2, it goes down 1 and across 2, okay? So D2 prime should go, let me see. So instead of down 1, it should go across 1, right? Yeah. Oh no, that's okay. Too bad. I erased it. So D2 prime goes from E to PQ. No, DR prime goes from ERPQ to ER. Q should go. Q should go up, right? And then P should go down. Okay, so that's DR prime. Okay, so D2 prime, it should decrease P by 1 and increase Q by 2. All right. Yeah. So D2 prime should decrease P by 1 and increase Q by 2. It should go here, and this should go there. Well, what is it then? I mean, because it goes into the 0 region, it has to be 0. Okay, so D2 prime is 0. And that means the cohomology doesn't change. Okay? This is also the picture of E3 prime. Mhm. But D3 prime, okay, it also goes into the negative region. It's even deeper into the negative region. So D3 prime is also 0. So in fact, dr prime equals 0 for all r greater than or equal to 2. And that means the spectral sequence doesn't change anymore. As you turn the page, it's always this page. Okay, so this is your E infinity prime. E infinity prime. And E infinity prime is supposed to be the associated Grady complex of the total cohomology of K. Okay, so now if you look at a given degree, let's say you look at degree K, when you look at a given degree, let's see what the filtration is. Okay, now I wonder whether green on green will show up. Let's see. Oh, well, it does show up, right? Yeah. So let's say this is degree K. Now degree K, these are the elements of degree K. Okay, but you see that the filtration on cohomology has only one non-zero term. Yeah. So if you just look at degree K, so E prime infinity in degree K, it is the associated Gray complex in degree K of the cohomology. But the associated Gray complex is the direct sum of these boxes. You've got only one non-zero term, so it is HK of M. Right? Right. And well, it's HKOM, but it's also, no, HKOM come from here. Right? It's E infinity. This is a picture of E infinity. And in degree K, you have only one box. And then over here, yeah, HD, that's also the picture of the total cohomology. And in degree K, you have only one box. Okay, so the total cohomology in degree K is the de Rham cohomology in degree K, because you have only one box. Okay? And so that's what you get from the second spectral sequence. Now, let's see what we get from this first spectral sequence. Oh, no, gosh, I erased K. Oh, no. Yeah. Oh, no. So C0U omega Q, C0U, no, C1U omega Q, and then C0U omega Q plus 1. Okay, now in order to calculate the vertical cohomology, we should assume that we have a good cover. So now you assume that U is a good cover. If it's a good cover, and you calculate the vertical cohomology, which is de Rham cohomology, everything will be 0 except in degree 0, right? So yeah. So we need a good cover in order to make the computation easy. Yeah. Okay. So the first spectral sequence will have E1 is HD. And then if we have a good cover, everything will be 0 except in degree 0. And in degree 0, I will just have locally constant functions on each open set. So that would be C0 of U R, C1 of U R, C2 of U R. Okay, so that's HD. And that's precisely the check complex. So E2 is H delta HD, and E2 will be the check cohomology. H0 U R H1 U R H2 U R. Okay. Yeah. And now D2 goes down 1 and across 2. So D2 is going to go from here to here. But just because it goes down 1, it has to be 0. And D3, D4, and so on. Okay, so yeah. So that means the third page will look the same as the second page. So D2 equals D3 equals D4 equals 0. And that means E2 equals E3 equals E4 equals E infinity. So this is a picture of E infinity. And E infinity is supposed to be the associated Grady complex of the total cohomology. It has only one term. So again, in degree K, E infinity K, it's just going to be the check cohomology in degree K. And this is E infinity. So when you filter the cohomology in E infinity, you also get only one term in degree K. So this is HK of D. Okay. And okay, so you get HK of D here as check cohomology, but using the other spectral sequence, you get HK of D as the Dom cohomology. And these two statements then give you the check Deron isomorphism. Okay, so 1 plus 2 implies that the Deron cohomology is isomorphic to the check cohomology. Okay. Yeah. So this is the simplest way of calculating or approving the check-the-ram isomorphism. It's just a very straightforward calculation, using the two spectral sequences. All right, now in the last homework, you spend a lot of time proving a couple of tic-tac-toe lemmas. You have to prove that some map that you define from H delta HD to H big D is well defined, and then has an inverse that's well defined, and that gives you an isomorphism. And like for different situations, you have different proofs. Okay, so now I want to use spectral sequences to prove the tic-tac-toe lemmas. Right? Let's see. Okay, so the first tic-tac-toe lemma we prove concerned the situation where HD has only one non-zero row or only one non-zero column. In a double complex. And so we said that if HD has only one non-zero row or one non-zero column, then there's an isomorphism from H delta HD to H big D. Okay. And I think, yeah, we did it for a first or second quadrant spectral sequence, but now I'm just working with first quadrant spectral sequences, so I will assume that I have a first quadrant spectral sequence. So let K be a first quadrant. Double complex. And this is a tic-tac-toe lemma. Yeah. Well, but you know that HD is E1. So okay, so we know that this K has a spectral sequence and has a spectral sequence, okay, with E1 is DHD. So it's there. And then E2 is H delta HD. Okay. Okay. So delta goes horizontally. H delta HD may not be the same as HD, but it can be non-zero only in this row also. Okay? And here, obviously, here is going to be the same as this because delta is 0. Okay? So, but in any case, it will look the same. the shaded area might not be the same, but it just indicates that it's non-zero. So E2 looks like that. And then, well, you know that D2 goes down 1 and across 2. And here D2, you know, goes across 2. So D2 is 0. D3 is 0, and so on. Okay? So D2 equals D3 equals dot, dot, dot. It's all 0. And that means E2 is equal to E infinity. Okay, so this is E infinity. And E infinity is the associated Grady complex of H big D. And again, in each degree, you have only one box. So that is going to imply, as before, that E2, okay, E infinity K is going to be E2K. And that is going to be H delta HD in degree K. And that is going to be the total cohomology in degree K. So you get this isomorphism, okay? And you see that the same argument applies to many different shapes as long as D2 is 0, right? So like in the homework, we had 2 other shapes. So example, in the homework, we had a shape that's diagonal. Say HD looks like this. But it's HD looks like that. HD, oh yes. And then, okay, delta goes across. So delta is 0. Therefore, this is also H delta HD. The thing about the spectral sequence is that the differentials, you know, gets extended, right? So instead of just D and delta, you have D2, D3, D4, and so on. And D2 is gonna go down 1 across 2. So anyway, D2 will be 0, D3 will be 0, and so on. So if you have a shape like that, D2, D3, and so on, they're all 0. So again, E2 will be E infinity. And then, so, and that will be G of H big D. And in each degree, you have only one thing. So, okay, yeah. Yeah, so E2K is H delta HDK, and that is going to be just HKD. Okay? Yeah. Yeah. So It's so simple now. And then we have this shape. We have this shape. Okay. And okay, so now that is HD. And then H delta will have the same shape, but the contents might be different because you have to take the kernel of this map and so on. So, but H delta HD has the same shape. And here again, you see that D2 is going to be 0. And D3 will be 0. So for the same reason, you're also going to get E2K is E infinity is going to be HDK, and E2K is H delta HDK. Okay? Yeah. Okay, so here is another tic-tac-toe lemma. So you see that the spectral sequence is a really powerful tool, that turns a lot of computations into a routine computation. And usually, it's considered a big machinery and difficult to understand. But yeah, I think I have shown you that it's not that complicated. Yeah. Okay, so let's take a break, and then we want to, we want to consider the product structure on a spectral sequence, and then also extend the Ram cohomology to vector valued forms. Okay, so I will see you in 10 minutes. Yeah, it might be okay for you, but I don't know about people watching it online. All right, okay. Okay. Okay, so the main thing to remember is that the spectral sequence gives you a picture of the associated Grady complex. And it's the boxes, it's these boxes in a given degree. And that doesn't give you the cohomology because in general, because what it gives you are quotients, successive quotients of the cohomology, Okay, yeah, all right. So now let's extend de Rham theory to vector value forms. And the reason we want to do this is that when we compute check cohomology, with coefficient in a sheaf, now if this sheaf is just R, then you know that for a good cover, this is isomorphic to de Rham cohomology. Okay? Now, the Ram cohomology is concerned with R value forms, but in general, this sheaf might not be R, you know. I mean, it could be, say, vector value functions. And so we need to extend the Ram cohomology to vector value forms in order to get a generalization of the check-the-Ram isomorphism. Okay? Right now, the check-the-Ram isomorphism only works for the sheaf, pre-sheaf of locally constant R value functions. Okay? But we need to look at vector value functions to extend this. So, well, I mean, it's really very straightforward. So let W be a vector space. Then a vector and no, and W, oh yeah, a W valued K form on a manifold M is a function omega that assigns to each P in M an alternating K-linear function on the tangent space with values in W instead of in R, right? So, okay, now how do we define the exterior derivative of a vector value form? It's very simple. If you choose a basis, yeah, you see, if you choose a basis for W, then you can think of a vector value form as just a column vector of ordinary forms. So let say E1 to ER be a basis for W. Okay, so that means I'm assuming that W is finite dimensional. Then a W value form, say, omega, then it can be written uniquely as, okay, the value of W, the value of omega is in W, and so that's a linear combination of the EIs. And the omega i's are ordinary forms. Okay. So you basically think of W as a column vector. You think of omega as a column vector of ordinary forms. And then like d omega is just, you take d of each component. Okay? And you show that this is independent of the choice of bases. And then you can define C infinity W value forms. It means that the omegas are all C infinity, the omega i's are all C infinity. And it will be well defined, because like when you change bases, you transform by constant matrix. So it's not going to affect whether the coefficients are C infinity or not. Yeah, so then you can define the Ram cohomology with coefficients, not in R, but in W. Okay, so all right. So so definition, then omega K M W, that's the C infinity W valued K forms from M. Yeah, and you can define the Ram cohomology with coefficients in W. Uh-huh. Uh-huh. Because you have D. Okay. Yeah. So it's the kernel of D from omega K MW to omega K plus 1 MW over the image of D from the previous omega. And basically, yeah, if you think of W value forms as just a column of ordinary forms, then the Ram cohomology will just be, like a column of R components, each of which is an ordinary de Ram cohomology. And yes, and then so then what is the Ram cohomology of Rn? Okay, say with values in W. Basically, you can work component by component. So you see that it will be 0 for K greater than 0. Because each component is just ordinary de Ram cohomology. And in degree 0, well, you actually have an invariant answer because it would be the the W value functions whose derivative is 0. So it would be the locally constant W value functions. Because Rn is connected, it would just be the constant W value function. So it would just be W in degree 0. Okay. And then we can generalize check the Ram isomorphism. So to W valued forms. So the check the Ram isomorphism okay, would say that for a good cover, U on a manifold M. So de Rham cohomology with coefficient in a vector space and a finite dimensional vector space W. De Rham cohomology with coefficient in W is isomorphic to the check cohomology of the good cover with coefficients in W bar, and that's the pre-sheaf of locally constant W valued functions. Okay, on the good cover. Okay. Okay, so everything that we have done before can be generalized to vector value forms. Okay. All right, yeah. We'll stop here. And next time,